Okay, let's get started, I suppose. 4:15. So it's a long recap. So we were looking at renormalization group flow of the Ising model, and the Ising model, with a long, painstaking journey, we figured out that at least t equal to 4 Ising model can be written as a scalar field with these three terms. And the phases of the Ising model, which we know that it has an ordered phase, and a disordered phase is described by the sign of mu zero square, which is the coupling strength of the phi square term. So if t is greater than tc, we sort of using experiments and so on intuited that this must be the case. So, and if that's the case, we'll get phi to be 0, meaning the average magnetization of the sample is 0, meaning all the spins are randomly aligned. That's the disordered phase. And when t is less than tc, mu 0 square is less than 0. And then we computed or convinced ourselves that the expectation value is one of these two. M0 is some non-zero minima of this potential. So when mu square is less than 0, u of phi as a function of phi will have two new minima, m0 and minus m0. So the system will pick one of them, and that's the ordered phase. All the spins are aligned this way or that way. And then, well, this is another recollection from the past. The steps of RG. There are three steps. One, the main and important step is to integrate out high moment. Yeah.
I don't know, this is very basic, but initially it was just 1 minima at phi
Equal to 0.
Right? And we're saying it's disordered.
Mm-hmm.
But we are saying it's ordered. We are assuming that all of them are aligned. Or is it like the average is M?
The average is m naught.
Not necessarily all of them are aligned.
All of them are aligned only at t equal to 0. Yeah. So I guess, yeah, the average is non-zero. We call it order. Yeah. So again, RG steps, a recap of that. The first step of RG was to take this field phi, decompose it into high momentum and low momentum modes, and integrate out the high momentum modes. So zeta is a value that's greater than 1, lambda is the cutoff that's within this. So this x cannot be less than epsilon, which is of order 1 by lambda. The difference between phi x, well, below this length scale, phi x is not well defined. And so that's the UV cutoff. So we integrate out high momentum modes or short distance modes, and then we change units of the position variable x to x prime such that, this should be here, such that so after we integrate out this high momentum mode, the new cutoff is lambda by zeta. We change units such that cutoff is lambda, and then we also changed the normalization of the remaining leftover field so that we can compare it with this half, right? We decided that we'll fix this coefficient for this problem. So far what we have done is just ignore the first step, ignore the correction to each of these couplings that comes from the first step, and just do steps 2 and 3 to see if that can tell something. That already told us that all the infinitely many coefficients are irrelevant in d equal to 4. So this was this we call the naive RG results was this mu square when we do steps 2 and 3 becomes zeta square mu 0 square. This is the initial value. So it just keeps increasing as we increase zeta, meaning we're integrating out higher and higher momentum modes, even though we haven't done it in steps 2 and 3. So that coupling, we called it relevant. And the lambda coupling changed like this. And when D is 4, it doesn't change. So we call it marginal. And last time, we wanted to do it in full-fledged detail. So we have to do this step, which is the toughest step. Last time, what we started off is just doing the first step. So decompose phi into plus and minus. And then the action we can decompose into plus and minus. So we decomposed it in this particular way. There is no given choice. We can do it in any way we want to. So this is how we did it last time. So the plus fields, which are the high momentum fields, we first wrote down the free part, meaning the quadratic part of the action. S minus is whatever, well, no zero. S minus is whatever only phi minus action that we can get from plugging this into here. And the interaction bit, which is the mixing between plus and minus, is just plug in that, take off this. Why did I take off this? Because we've already included it here. So when you add all of this up together, we just get back this trivially, right? And then we want to integrate out the plus fields. So when we find the partition function, we integrate d phi minus and d phi plus of e to the minus action. But we first want to integrate out this guy only. And this we call it some new action, S tilde. And our goal is to find out what S tilde is. So just plug in S in this form. S minus just comes out because it doesn't have any pluses, of course. And then what's left is integral d phi plus e to the s plus 0 s int. So this thing, if you remember, is just expectation value of this operator with respect to this free action, right? So taking a log, we get, and putting a minus sign, s tilde is nothing but s minus log of this thing, right? This angular bracket just means this specifically. So when we did steps 2 and 3 only, what we actually did is to just ignore this bit. But that's what we are going to compute now. So yeah, we actually computed this, right, to one loop. I think we did. But let's recollect it very quickly maybe. So yeah, log of e to the minus s int plus is nothing but log of 1 minus s int plus s int square by 2 factorial dot dot dot, and log of 1 plus something. Whenever we see that, we expand it without even thinking. So this is approximately minus s int plus, this plus just means that expectation values with respect to this free action, plus 1 by 2, right, yes, 1 by 2 s int square plus minus s int square plus. Is this clear? So this is basically what's going on. Minus x. So take this as x, then we have this plus this, and x square is coming from this square. And the signs I may have messed up. Yeah, but that's it. So we computed this, I guess, s int. So this is easy to compute because when we expand it to the fourth power, we would have a term with 1 phi plus and 3 phi minuses. But if we have only 1 phi plus, expectation value under this is 0 because it's quadratic and blah blah blah. If you have 3 phi pluses, same answer. If you have 4 phi pluses, well, that doesn't contribute to an action for phi minus. It's just going to be a constant, be it infinite. So we ignored it. So the only term that we had to compute was phi plus, phi plus, phi minus, phi minus. So schematically, here we had, okay, what's the coefficient of that term? It's binomial expansion, that's 6, right? 1, 4, 6, 4, 1. So s int plus we computed, and that was 6 lambda 0 by 4 factorial integral. Just write this in momentum space. K1, K2, K3, K4, 2 pi d delta d sum over I, Ki, then phi minus K1, phi minus K2, expectation value phi plus K3, phi plus K4 plus. Is that, do you remember all of this? And then we decided, oh, when we plug in the 2-point function, which is just 1 by this times delta of K3 plus K4, and shrink the delta functions and so on, what we end up is with some Feynman type rules. So whenever we see this contraction, we decided that we will draw a dotted line. Whenever see phi minuses, we will draw external lines, dash, well, non-dotted lines, just lines. So we would draw this picture like this, with the vertex having the rule that it's 6 lambda 0 by 4 factorial, and momentum is conserved at the vertex, and incoming momentum K1, incoming momentum K2. And momentum conservation tells us that this must be minus Q1, right? And this loop integral, well, this extra thing becomes integral over Q of the propagator, right? Which is 1 by Q square plus mu0 square. We did this computation last time. And we just called it I, some integral in d dimensions, a function of zeta.
Yeah, I missed last time, so if you can't answer this quickly, then it's fine to move on. But I'm not seeing how you get this because you have like lots of different terms if you expand that 5 plus plus 5 minus 4.
Right, so you would have phi plus phi minus cube, that's 0 under the expectation value. Phi plus square, phi minus square, that's what we took.
Okay.
5 plus cube, 5 minus also 0, and 5 plus 4, but that's a constant, doesn't contribute to 5 minus action.
That's a constant. Oh, right. Yes, okay. I see.
Right. So that's infinite, but whatever. Yeah. So only term is this. So this is going to be 4 times this, 6 times that, 4 times that. Yeah, 1 time that. Yeah.
And that's what it's.
Right.
I see.
Right. And these momenta are shuffleable because of the delta function. So, right. So in the end, let's erase something. Everything seems to be needed. Let's erase this thing. No eraser. Yes. So in the end, what we see is that mu 0 square. So what's S minus? S minus is basically this, right? What this term tells us is that phi minus square term gets a correction, right? And this is indeed the correction. So what we have is mu 0 square coming from S minus plus this extra guy at first order. Let me make sure the sign is correct. Right, so we have plus lambda 0 by 4. I just deleted the 6 and 4 factorial to get the 1 by 4. ID of zeta. Is that clear? So we just did step 1, right? So when you do step 1 again, mu 0 square from this for the phi minus square term. From this, phi minus square gets this extra correction, which we just added. So in S tilde, this would be the coefficient of the mu 0 square, sorry, phi minus square term. And then we do steps 2 and 3. It has no change. Gives you that.
So there's no big lambda dependence. Yeah.
Big lambda dependence is what? There is a big lambda dependence. Big lambda dependence. That would be in here.
So that should be zeta
and lambda, yes. Which we would compute in a few minutes. So lambda 0, meaning the phi minus 4 term, do not get a correction, because from this single term, you cannot have a phi minus to the 4 term with additional phi pluses sticking around, right? So that's where we left off. Now we compute this. Also, I think I mentioned that this thing is called a cumulant, meaning if you are drawing Feynman diagrams, you do not have to look at disconnected diagrams. So we'll see the example right now. Can I erase this? I think I can erase this. So we are going to compute this guy. So let's focus on S square expectation value. So we take a square of this guy. So meaning a square of this guy, and find terms that's important to us. So there will be a correction to the mass term one more time, right? You can think of, for example, taking this times this in the square. That will have a phi minus square and then a lot of phi pluses. So how many? 6 phi pluses, which can be integrated. So the Feynman diagram for that would be, let's try to think about it. You must have two external legs. Then something like that.
The vertex has like 4, 5 pulses, right? Or 6, 5 pulses.
Yeah. So
A single vertex with 6, 5 pulses. Join at different points.
no, that vertex not necessarily have. Yeah, I think you're right. Yeah, I'm going to ignore the mu0 correction because we don't need that to find the RG flow to first order. Because the question is for this guy, right? It's marginal in naive sense. So under the first step, is it going to be relevant or irrelevant is what we actually want to find. So it is important to find the correction to mu0 square as well at this order. And I think that's the correct diagram that would appear because it has to be two loop, right? So we would end up having phi minus with phi plus, phi plus, phi plus, phi plus, 2, 3, 4, 5, 6. Yeah, 6 of them. I'm getting confused about that though.
And then we contract.
You contract.
So there's many contractions.
Yeah, there are many possibilities. So I guess we can work it out at some point, I guess, or leave it as an exercise. So one diagram that should appear is this, a two loop. This is a correction because it's a phi, solid lines are phi minuses, so this is a phi minus correction that would appear. Another diagram that can appear is, let's say this. And probably other diagrams too. But let's just forget about it and think about phi minus to the 4 corrections because it didn't receive any correction at one loop. You're seeing if it gets a correction at, sorry, yeah, that's right.
So mu square is a function of sign cutoff.
Mhm.
And the way we found that correction is by second and third step suggest how it changes as you scale. Right?
Yeah.
If you do the first step and then you do the second and third step, does it affect anything or?
No, we actually derived this general result long time ago that mu0 square is scaling thing plus RG step 1 thing. So it doesn't affect anything. So this is just scaling of position only. There is an effect from this which would add an extra thing below this that depends on if the kinetic term picks up a constant or not, which it does at when we calculate, for example, this diagram. It does pick up a constant, but it will be higher order in when we expand it out. It's going to be higher order in this, I guess. So we are ignoring it for now to just get the leading order flow structure or leading order phase structure of this theory. Right. So to compute corrections to lambda 0, we only have to look at phi minus to the 4 type terms. So we can just think of diagrams, right? For example, we will have a diagram like this. Right? Take the square of this, and then there will be 4 or 5 pluses. Contract them in the previous way. For the mass correction, we contracted it in a particular, only way that's possible. And then you'll have just 2 copies of it. So that's what I meant by this. But that's going to be cancelled. So that's the meaning of all the disconnected diagrams. Like, so this is a disconnected diagram because it's not connected, obviously not connected. So this will be cancelled from this. You only have to look at connected diagrams. So I leave it as an exercise. Take the power of this, second power of this, and then contract it in a specific way to derive this diagram. This is a connected diagram, and this is some non-zero term that's going to be here. There is another possible diagram, just like this. Right? So this is like a phi plus to the 3, phi minus vertex, phi plus to the 3, this vertex. But this diagram is 0. Can you identify why? Exactly. So this solid line must have momentum in this region, but the dotted line have momentum in that region. So the momentum conservation imposes that this line has the same momentum as this line, which is never possible. Right? This line and this line must have the same momentum. They come into each other, so they cancel. So this diagram is just 0. And there are no other connected diagrams. So we can compute it in the sense that we can derive this from taking the second power of this and so on. But it's probably intuitively clear, right, that you would get a term like this. So we can compute it now. We took a square of this, so we have a 36. So we would have, so let me just look up the numbers correctly to not mess it up. Right. So we just have to take a square of all of this, lambda 0 by 4 factorial times 6 squared. Each vertex comes with that factor, like here. So that's going to be lambda 0 square by 16. Right. Then we would have integral k1, k2, k3, k4 for the external lines, 2 pi 4, 2 pi d, delta d, sum over I, ki. So this is like 1, 2, 3, 4, and let's call this q. So this must be q minus k3 plus K4. Right? So that's the next integral. Integral over Q, 1 by Q square plus mu 0 square, Q minus K3 plus K4 square plus mu 0 square.
So is it K3?
Yeah. So let's just call this something. So this is, let's say F D zeta and lambda. So why is the lambda coming in? Because this is d dq, and the integration limit is from lambda by zeta to lambda, because this is only the 2-point functions of the dotted guys, which is here. And remember, 5 plus is restricted in this region. So all these integrals are finite.
So it's the thing, the total thing, including all of them?
No, just this guy. Yeah.
So
Right.
then depends on K.
Oh, it depends on K3 and K4 as well. Yes. K3 plus K4, which I will drop in the sense that, K3 and K4 are smaller than lambda by zeta. So the first order, set it to 0. Just an approximation. You don't have to do it, but we just do it for simplicity. So I'll define this to be approximately lambda by zeta to lambda q by 2 pi d 1 by q square plus mu 0 square square. All right, so we have figured that out too. So from S minus, we have this full term. And then from here, we have this term, right, which we plug in here. And then we see that this modifies to lambda 0. I cannot remember the numbers. Can probably figure it out, but yeah. Minus lambda 0 square by 32 f d zeta lambda. I'm not sure if I messed up the numbers. I'm confused about this 4 factorial now, because the 32 is just coming from 2 times 16. But this 4 factorial is taken out, right? So should I multiply by 4 factorial or not? I'm getting confused about that. So the sign is negative because of this. Previously it was positive because of that. In the mu correction, there are 2 negatives that cancel each other, this guy and this guy. So there is a 4 factorial maybe missing here, but it's not going to take away from the discussion. So let's forget that there might be a numerical error.
So there's FD, it has mu not in it too.
Yeah, it has mu naught in it too. It depends on mu naught too, sure, which we will figure out now, right? So from this, we learned something immediately. If d equal to 4, previously lambda was marginal, meaning it didn't change as we increased zeta. But now we see that it decreases as we integrate out higher and higher momentum modes. Meaning in the infrared, meaning at the long distance for the long distance physics, in d equal to 4, lambda is irrelevant, right? It drives itself to 0.
So if I don't drop this momentum transfer, how do I think about this? Is that some sort of like non-emergence of start with a local interaction and you try to hide on until you get some non-local interaction?
Yeah, I think that's the idea. We can just expand it in as Taylor series.
So
Yeah,
that would, I guess, give you corrections.
that would give you corrections to, for example, what would be it? Gradient square acting on phi minus 4 or something, right? But that's irrelevant. We already discovered.
Okay.
Yeah. Is that his question clear? So yeah, his question is what happens if we include this? So imagine that we Taylor expand this. So the first order term is this and the next order term is this squared. So momentum squared means in position space derivatives, right? So we would be adding gradients to, oh shit. Here we must have, phi minus, phi minus, phi minus, phi minus, k1, k2, k3, k4. So that squared multiplied by this means that we are taking derivatives of this thing. But long ago, we've discovered that taking derivatives for the phi 4 term makes it irrelevant. So this is not even an approximation. We can take it to be exact effectively because everything else is going to be irrelevant.
Yes. So setting those k's to 0 is sort of analogous to that we also don't look at sort of emerging phi 6 terms.
Right, exactly. Yeah, that's a good point. Right. Now let's erase all of this and understand more about some more physics from these two equations. These two relations, by the way, are called the beta functions for historical reasons. And this tells us the phase structure of the theory. So first of all, what we do is we just approximate these integrals, right? Let's assume that zeta is 1 plus s with s very small. Is that something going on? Wow, okay. Do you have a class here?
Yeah, we do. Yeah, 9 minutes, sorry.
Okay, let's start from this. And
Oh, you didn't put the dependence of big lambda in the integrals.
so let's take zeta to be very close to 1. So we can take this to be sort of in the sense that it's a differential equation, right? So we can just, this also allows us to compute these integrals approximately. So I d zeta, if you remember, was lambda by zeta to lambda dq by 2 pi d 1 by 2 plus mu 0 squared. And if lambda by zeta and lambda are close to each other, this is approximately omega d, which is the angular thing, divided by 2 pi d. Let me also put that into omega d times the value of this function at either of these points, which would be just lambda 2 b minus 1 by lambda squared plus 0 squared times the length of the interval, which is lambda times 1 minus 1 by zeta.
Why is that
This is q to the d minus 1 angular part. Angular part is this. Then put all q's to be just lambda, absolute value of q to be lambda, and then length of the interval.
So this lambda is the lambda from the second one?
All the lambdas are the same lambda.
It's the cutoff.
It's the cutoff. Yeah.
All of them.
Yeah.
Yeah.
Oh, not these
Not
lambda.
lower.
This is the
coupling.
this is the coupling.
No, all of them in the last one.
All of them in the last one are the cutoff. Big lambda. Right, so this is nothing but omega d. Zeta minus 1 is what? S by my zeta and s looks the same. Zeta s by 1 plus s lambda d by lambda square plus mu 0 square. Right, and s is very small, so we are going to approximate it to be right. Now also fd zeta was lambda zeta lambda dq to power d 1 by q plus mu 0 square. Right, we had two propagators in the loop, so that's the square, and the rest of it, as we discussed, is irrelevant colloquially and technically. So this is equal to, again, omega d lambda to d minus 1 by lambda square plus mu 0 square times length of the interval, which again gives us approximately omega d times s omega d lambda square plus mu square. All right, so let's plug this in here, and then we can compute this. So this is nothing but mu 0 square 1 plus s is equal to 1 plus s square, which is nothing but 1 plus 2s, and so on. Mu 0 square at 1, right? Mu square at 1.
That's mu 0.
Mu 0 square, of course. Plus lambda at 1 by 4 times id, which is omega d times blah blah blah, omega d s lambda d by lambda square plus mu 0. That's it.
mu 0.
Mu at 1.
Yeah, okay.
Right, and then we can find, this minus this divided by s.
It seems like it's a discrete differential equation or something.
Yeah, s is small. This is the definition of a derivative.
Yeah.
How do you find that is?
Multiply 1 with this, then take it to the other side.
mu 1 in the denominator there as well.
Mu 1.
You did not that?
Yeah.
In the second term.
That's fine, right? So we have mu square 1 plus s minus mu square at 1 divided by s is equal to what?
So you keep part of mu 1 on the right hand side anyway.
Yeah, that's fine.
Okay.
That's fine. So we get 2s mu square from this, and 1 times this, because we already have an s, we cannot take this, right? So the s is gone because we divide by s. We have omega d lambda by 4 different lambda to the power d square plus mu square.
You're setting s to 0.
Yeah, now taking limit s to 0 because it's just small. So basically this is d mu square by ds. So let me just write it here. That board was awesome because we had a lot of space. So now I'm going to just do some rescaling to make this equation wonderful. First, let's do d equal to 4, which is the first case that we wanted to look at. And then define dimensionless variables, basically. So we would define mu square. Mu square, remember, from this we remember has mass square dimensions. So the only thing that mass dimension is lambda square times y, just a new variable. And similarly, well, lambda 0 in 4 dimensions is already dimensionless, but we would define, yeah, this is nothing fancy. This is just random coefficient punched into x. Yeah. So that I can draw the xy plane. That's my point. So if you put lambda square here, lambda square here, lambda square is y here, then the lambda squares cancel. D equal to 4, meaning you have a lambda to the 4. So lambda to the 4 becomes lambda square. Pull out the lambda square here. All the lambda square, of course, it cancels because these are dimensionless variables. And we end up with these two excellent looking differential equations. Yeah. dx by ds equal to minus 1/8. So we have to evaluate omega d, angular integral for d dimensions and so on. Look at that. That's simple. That's Dima's question to answer. So let's just see that the features are there, right? So the square is basically this square. And we have it's multiplied by lambda square here, which becomes x square. 1 plus y square is nothing but 1 plus y square coming from here. So it has the structure, and the sign is of course there. And there is nothing from here. Why? Because this went to the left side to make this derivative. Because there is nothing from here as well. Right? And this is basically what we see here. 2 mu square. This become x by 1 plus y. So how did we get this definition of x? Just bunch all these coefficients together. That's it. All right. So we know how the couplings change as a differential equation. So increasing s is we integrating out more and more fields, right?
But it shouldn't, we assumed it's small, right? So we can't just increase s.
Yeah, we cannot increase it arbitrarily, but
And these integrals would change their value, right?
the integrals wouldn't change values, but we would have additional terms. Well, we should consider additional terms, I guess, even if we don't.
Wait, does s have to be small here? So deriving this
Small at this point, s doesn't have to be small.
Yeah. I'm trying to think.
Yeah, this is just true to order, lambda 0 square or something. That's all we have to.
Why does it not? Because we definitely use the fact that s is small to get these ID and FD.
Yeah, but these are the rate of changes, right?
It just tells you where to go, like immediately after that.
Yeah.
You just follow that throughout
Yeah, it's just local.
Yes.
So locally you move wherever and then use the equation again, move
Yes.
again, and so on.
Okay. Yes.
Yeah,
So
but
if at some point you can prescribe what you want initially, no?
at what point are you thinking?
So
For
yeah,
large
so,
S, let's say.
yes, if you did like right, because you have S equals zeta minus 1, right? But if we then set, or sorry, 1 minus zeta, right?
Zeta
1 minus zeta.
1 plus S.
Yeah, S is, zeta is 1 plus S. So S equals zeta minus
So
1. Okay.
this is the correct thing to do. Zeta is e to the S approximately 1 plus S.
Yeah, that's what I was thinking. Yes, right. So if instead we did zeta equals e to the S, then
Yeah.
this would be exact.
Right.
Okay.
And we derived it for small s.
So you derive it for small s, and then you say use some group structure.
Yeah. Exactly.
Some group structure.
Exactly.
Exponential.
Which I don't know exactly how to argue, but
Ooh,
at the moment, but it can be argued, I guess. Just use this instead.
okay.
And then, well, even then to derive the differential equation from this, you of course need to take, how do you get a derivative? You need to take limit s tending to 0, blah, blah, blah. So, yeah.
Okay.
Yeah. But anyway, we are not going to look at the flow everywhere. We want to look at the flow close to the critical point only. So let's recall old lessons. At the critical point, well, remember what the critical point was? The couplings, relevant and irrelevant couplings all go to 0. Marginal couplings can be anything. But we have discovered that we only have relevant and irrelevant couplings in the game, no marginal couplings. So all of this should go to 0, or the couplings themselves should not change at the critical point. Meaning, at the critical point, the flow should not happen. It should be static. How do you find if the flow is static? Oh, if the rate of change is 0, right? So when is the rate of change 0 from this? At what x, y? Fixed point. Exactly. And that's the only fixed point for this system. And what we do next is also something that Dima would be an expert on. We would linearize the flow around the fixed point and try to solve the flow exactly close to the fixed point. So if you linearize, well, from here you get nothing because it's already quadratic. So dx ds is 0 close to fixed point, and dy ds is 2y plus x, right? And now this can be solved. Let me just write it in some matrix way. Just same two equations written in the matrix form. And to solve it, we just have to diagonalize this matrix. For that, we just need to find eigenvalues and eigenvectors. So we have this eigenvector with 0 eigenvalue. Just find it. I'm just going to quote it. And this eigenvector with 2 as the eigenvalue. Right. So we were wrong to say that there are no marginal couplings in the game, because we see this combination of variables do not flow, right? its eigenvalue is 0.
Well, that's only in the linear region.
Yeah, very close to the critical point. So if I make a plot, x versus y, and y, remember, was x, remember, was lambda 0. We decided it's always positive to make the theory stable. Otherwise, the lambda 5,4 term would be going down at some point, and it makes it unstable. So very close to 0, which is our critical point, there is this direction, which we can think of as twice x hat minus y hat. So that's like twice x hat minus y hat, something like this. Very close to, so all of this plane is close to 0, 0. So this is zoomed in. Here, along this direction, no flow happens. But 0, 1, the eigenvalue is 2, right? So what that means is if you perturb along 0, 1 direction, it just increases exponentially. The solution is e to the 2 times whatever.
Yeah.
So
that's is that the relevant mass coupling? Is that what that's representing?
yeah, so here we have one relevant coupling that flows like this. Right? And this direction do not have any flow.
Well, it's not exactly true because again you're in the linear region.
Yeah, that in the linear region, that's true. So if you go to the second order, I guess it flows towards 0, 0, right? Because it's negative. So I think that's the correct way to put it, I think. So you have, in the linear regime, we already knew that it's marginal. There was one marginal direction.
So I guess what this tells you is if you start with zero mass though, and you perturb lambda, but you don't also project the mass, then the mass term will eventually blow up or something.
Correct. So if we start with 0 mass, but have some lambda, then it would diverge to infinity. But if we start with a 0 mass and add the correct amount of lambda, which is along this line, then we would flow back to the critical point. Anywhere else you start, you just flow to infinity. I don't know exactly if this is the structure of the flow, but I'm just making it up. And here, to have continuity, it flows down. So we see that this line separates the behavior of the flow.
Oh, okay.
So above this line, we have one phase.
Right.
Below this, we have another phase. So if we think of the physics problem, we have some system which has some microscopic parameters. So let's say we take the liquid vapor. Let's take the magnet system. And when we start, the microscopic parameters are here. Let's say. Then what happens is that the mass term becomes very large and positive, meaning it's in the ordered phase. However, we have a knob, the temperature, that we can control. And we control the temperature, we lower it and lower it and lower it and lower it, and suddenly we hit this line. The moment we hit that line, we flow here to the critical point. If we decrease it even further, we flow to the other direction and get to the ordered phase.
I'm a little confused by this physical picture. So the knob
is the temperature.
Right, and the temperature will move us along the xy plane. But then if, let's say, I let the knob go, the system will on its own do follow this phase portrait.
Yeah, the phase portrait is, you have some microscopic model, but what you're observing is some large distance behavior. So turning this knob should be thought of, roughly speaking, as changing the microscopic parameters. But what you see in the infrared is sort of the same. So this flowing is the renormalization group flow. The system is not flowing to anywhere. It's what we observe is, yeah, it can be described by this flow. This flow lets us understand what we observe in the infrared.
I'm a little confused.
So the physical system, right, is if you heat up the magnet, it's disordered for some reason. But then if you cool it down, you hit a critical temperature, it becomes ordered.
Yeah. Okay.
So this is the explanation, I guess.
So you will only see physically the macroscopic system will be at the end of this flow somewhere.
That's what I was thinking.
Yeah, but if you're randomly here to start with the microscopic parameters, then roughly speaking, the mu parameter becomes positive infinity, or very large and positive, meaning the minimum of this effective parameter, so ordered phase. But now if you reduce the temperature to here, then it becomes negative, very large. So you have, in the rough picture, you have two minima and it's in the ordered phase. That's again at the end of the flow. But now if you somehow manage to reach here, then the end of the flow is here at 0. That's the end. It's ending there, right? So that's what you see at large distances. And that's a critical point. So this is, roughly speaking, the phase structure. In the first lecture, we mentioned that there will be a line that separates the phase structure in the coupling space, and this is that line. This is why I invented a color chart. There's one more thing that I want to do very quickly. Okay, you should ask more questions if you're confused.
Yeah, I need a little more information about what the,
Can I ask some questions? So it sounds like, okay, so if you start at some point that's not on this line or whatever, and then you say the physical thing that you are observing in the actual system is at the end of this flow. I mean, the flow in principle doesn't end.
Yeah.
If I take S to infinity, my mu or mu squared blows up either plus
or
infinity
minus
or
infinity.
In either case, it seems like, so plus infinity, you say, okay, that's disordered, minus infinity is ordered, because positive is ordered and negative is, but either way, it's going to infinity, so it seems like the field theory stops actually describing the system. So can I just say then that what you observe is the end of the flow, provided the end of the flow sort of makes sense.
Yeah.
Otherwise, if the flow diverges to infinity, what that means is you're not observing a statistical field theory. You're observing the Ising model at some random temperature, which is not the critical temperature, and so it's not going to be the same as some other thing in the universality class of the Ising model that's at its own temperature, right?
So this flow, you think of it qualitatively, that qualitatively what you expect is positive mu if you're here, meaning disorder, and negative mu order.
Yeah.
So we shouldn't continue this flow down to infinity and then say, oh, it's true to all S, which is obviously not the case because we have to be careful and so on.
Yeah.
Well, S is supposed to demarcate which one you consider as high energy modes and which one you consider
Yeah.
as low energy modes.
Yeah.
So it's not like it's an S to infinity.
Right.
Um,
Then you're basically thrown away everything.
Right.
okay, yeah.
So again, this is qualitative in that sense.
Right. So and that makes sense in the sense that, like, if I have a nearest neighbor Ising model versus a next nearest neighbor Ising model, and they each have their own critical temperature, but if I'm at, square root of pi times that critical temperature, I don't expect those two to look the same, right? Whereas at the critical temperature, they would look the same, so they're both described as a field theory. But also it's true that if I'm very close to the critical temperature, then I still should look mostly the same. Like, there should be some sort of order of limits I can think about, right?
Mm-hmm.
But I'm having trouble thinking of that order of limits, where I take the temperature very close to the critical temperature, so that I have a very, very small mu, so that, like, mu is much, much, much smaller than lambda, right? So that I can forget about the cutoff and look at a real continuum field theory, but with finite mass.
Mm-hmm. Mm-hmm.
And that should work whether I'm dealing with Ising model nearest neighbor or with next nearest neighbor. Yeah.
Yeah, I guess what you're saying is
I don't
this.
see how to do that order of limits where you take S really large, but
Yeah. I guess what you're trying to emphasize is that this picture only holds very close to the critical point, and what you want to do is start very close here, and then the flow will be very slow. So even if you take S to be very large, you would maybe end up here.
the flow will be very slow. Okay.
Yeah. Because it's logarithmic, right? For the lambda at least.
Maybe that's what I'm missing.
Yeah.
So near the critical point, I can evolve S by like 10 billion,
and
I still don't move much.
Move much,
in
yeah.
the XY plane.
Yeah.
Okay.
Yeah.
Okay.
I guess that has to be the answer.
Okay.
Yeah. You have any other questions? If not, I want to do one more flow diagram.
Yeah, you can. Yeah, why don't we do that?
Yeah. So that's going to be. Let's not erase this. So we previously mentioned that three-dimensional Ising model, we cannot do this effective theory approach because we have too many relevant couplings and too few knobs to turn. However, from this, we are going to do some crazy thing and get a qualitative idea about the phase structure of the D equal 3 Ising model. And the crazy thing is this. We take D to be 4 minus epsilon. As always. So we are going to look at Ising model in 3.9 dimensions, which absolutely makes no sense, but we can kind of make sense of this analytically at least. So if we are not at D equal to 3, but very close to D equal to 4, then 4 minus D is what? 4 minus D is epsilon, right? So this lambda term, even without this guy, becomes relevant. As we increase zeta, be it very slow, lambda increases. So we have this relevant parameter. Sure. However, but all the other terms like phi 6, phi to the 5, all of them stay irrelevant if epsilon is sufficiently small. Then we can do the same game, which I can maybe skip, right? And figure out the differential equations. So it's going to be almost exactly the same, right? What's going to be different is that for this guy, there will be a term from this times that, right? Just like we had a 2 times mu square, we will have an epsilon times lambda, which in this x variables is this. I think that's it. That's the only change.
What about the second?
Second one, we didn't change anything, so it should stay exactly the same. Right?
Yeah, I guess ID and FD wouldn't matter.
There were no D in definitions, right? It was Y.
Yeah, ID and FD. Well, let me just write this too. So the variable changes are mu square equal to lambda square x, y like before, and lambda by 4 omega d is equal to lambda epsilon x. So lambda now has dimensions of mass to epsilon, right? So this is the correct dimensionless variable. If you plug this change in, then the change in FD and ID would be absorbed into these definitions.
I see.
Just
right.
yeah,
Sure.
it's very simple to do it. Yeah. So this has, well, 0, 0 is still a fixed point. But amazingly, it has another fixed point. And that's called the Wilson-Fisher point.
I have a question real quick.
Yes.
Is this equation accurate only for small epsilon, or is this
Small
just
epsilon.
generally true?
Small epsilon.
Okay.
Yeah. So, yeah, Wilson-Fisher. Try to equate it to 0 and so on. So, x star, y star, approximately equal to. It's very hard to find it exactly, so it's very easy to find it approximately to first order in epsilon. And this is equal to 8 epsilon minus 4 epsilon. So this is like here. 8 epsilon minus 4 epsilon, somewhere here. Right? And
it's in the same line as that one.
it's in the same line as that.
2 minus 1.
2 minus 1, I guess. Yes, that's right. Yeah, that's a good observation. Now, just
That line also is different now, no?
yeah, the analysis around 0, 0 stays the same, right? Because it's the same.
Yeah.
We are linearizing around 0, 0. Now we should linearize around this guy. Let's say xy equal to 8 epsilon minus 4 epsilon plus delta x delta y, and find linear equations for the delta x and delta y. I'm going to skip algebra again for the sake of completeness. Do this as a homework. So we just have to find the Jacobian to do it quickly. Dima would explain this at some point. Yeah, of course. And then the flow is dictated by the eigenvalues of this. And we can already see the eigenvalues. These are minus epsilon and 2 minus 8 epsilon. Right? One eigenvalue is negative. One eigenvalue is positive. So let me erase stuff. So if we again make a plot of this, x, y. Oh, yeah. There is a change here actually. Because of this epsilon term, it's going to be diverging, right? So this term will diverge in that way, this way, and that way. So it's going to be divergent everywhere. But there is this extra Wilson-Fisher point along this line that has one negative eigenvalue. We just have to find it. So minus epsilon eigenvalues corresponding to, like before, 2 minus 1, the same direction, and 2 minus 8 epsilon corresponds to 0, 1. So at this point, this direction is a converging flow because of negative eigenvalue, and this direction is a diverging flow. So if you start from this point, you stay at that point because it's a fixed point. But you start anywhere else, you typically just flow to infinity. But if you somehow start along this line, then you flow towards the Wilson-Fisher point. If you are away from this as well, you still flow towards the Wilson-Fisher point, but because of this direction having a convergent flow. But if you are along this direction, well, let me just draw this, then you diverge. If you start here, for example, well, now just fill in the arrows. You go here, you go here, you start here, you go here. If you start here, well, this is also a diverging flow. That's the flow. Now compare and contrast with this.
Why is it toward this and not towards 0 again?
Yeah, there should be lines like that too. I mean, I'm not solving it exactly. I'm just drawing
So
it.
there will be some
yeah.
Sorry, what do you mean?
like asymptotic to y-axis, something like that.
Yeah. So, yeah, things like that.
Oh, okay.
Yeah, I don't know exactly how the flow looks. I'm just qualitatively drawing stuff. So we should have had a color chalk. So along this direction, we have a converging flow. Along this direction, we have a diverging flow. So let's think about the physical picture again. If we are random, if you take a random system, we start at some point. Then, well, we have, yeah, and then we reduce the temperature to hit somewhere in this line. And then we flow to the Wilson-Fisher point. Right? So for d equal to 3.9999 dimensions, we just have to turn one knob to hit the critical point. Right? Naively, from the effective field theory perspective, what we thought was we have too many relevant parameters and we don't have enough knobs to turn. That's actually not true. If you are in 3.999 dimensions, we only need to turn one knob, which we take it to be the temperature, to hit the critical point. So what we now do is the next crazy thing. We take epsilon to be larger and larger, right? So qualitatively speaking, as epsilon increases, this thing becomes larger and larger, right? So it becomes further along this line. We imagine nothing dramatic happens. And even at epsilon equal to 1, the flow structure remains.
I have a question.
Yes.
Right, so for d equals 3, so epsilon equals 1, if I'm recalling correctly, we looked at the thing and we said, okay, we have 5 squared, 5 fourth, and 5 to the 6th term, and we can't like tune all the things.
Yes.
Um,
So that, remember, was we were analyzing around this critical point, essentially. This fixed point, essentially. Around this fixed point, we have too many relevant directions that we cannot tune. So this is another exercise that we should do. Maybe I'll do it next week. That at the Wilson-Fisher point, you only have one relevant direction.
So even at epsilon equals 1, you expect
all the
dimensions
other
in the phi 6 and everything else
Yeah.
will also be.
also be irrelevant, and which can be shown.
Okay, so then my question is, so this was written down for small epsilon, but can we do this exactly for not small epsilon and show that there's this fixed point?
No,
Not even for like epsilon equals a half or something.
I don't think so. So people know that there is a fixed point analogous to the Wilson-Fisher from numerics. So what we have done is just qualitative.
So does this fixed point, I'm having trouble understanding orders and limits, I guess.
Yeah.
Because epsilon has to be small, so this fixed point is close to 0, 0, but we're expanding around each fixed point separately.
That's close.
Yeah,
But the expansions are not the same,
right.
so something's going on. Weird.
Yeah, these two are close to each other, and the expansions are consistent, right? If we are close to this, then we see everything is diverging, which we see from the expansion as well. If we are close to expanding around this, then there is one direction that's converging. So I think that's consistent.
But if I write the differential equations for epsilon equals 0.001, there's only one fixed point, or there's two fixed points?
There are two fixed points.
Yeah, even if I don't drop order epsilon squared term, so I keep order epsilon squared, epsilon cubed.
Yeah.
Are there one or two fixed points?
Two.
Okay.
People apparently have done it to order epsilon 5.
What about just to all orders in epsilon? You can't even write the differential equation, or is there no fixed point?
I think there still is the fixed point, but I don't think you can write the equation, differential equation,
Okay.
exactly.
Mhm.
Because you would need to do higher loops maybe to.
Well, that's what I'm wondering. Is the loop expansion seems unrelated?
Yeah, unrelated to this. Yeah.
Expansion.
Yeah.
Oh, but if you have large, well, never mind.
So if you have just epsilon equals 0.3 or something, you would still only have two dimensional coupling constants, 0 dimensionless, and and sort of a bunch of 1 over, well, two positive dimension coupling constants, 0 dimensional or 0 non-dimensional coupling constants, and a bunch of negative dimensional coupling constants. So you'd still have two parameters.
So at the Wilson-Fisher, you only have one.
Right.
One relevant direction, which is this. Which is again, parallel to temperature.
What about other dimensions?
Other dimensions, as in 2-dimension, for example.
7.
7 is easy because it's essentially this.
I will not get more points.
No, because if it's 7, it's going to be zeta to 4 minus 7 lambda 0 blah blah blah, right? So this is negative.
Okay, 3.
Yeah, this 3 is what we're talking about now.
3.5, I don't know. Is there any other ones where I can have more points?
Yeah, d equal to 2, you have infinitely many points.
Can I have 3 points?
No.
D equals 2, you have infinitely many?
I think that's the idea. And then with each
you only have the